Okay, so next we're going to have Luigi from University of Salerno. He's going to present his work on SYCL-Bench.
Hello. So let's talk about the SYCL-Bench. First, just a small introduction about some background about our work. Like original SYCL 1.1 was it's been designed as a high-level programming model on top of OpenCL, so it was kind of tied up to the OpenCL as a language. Since the last SYCL specification on SYCL 2020, it has been allowed for third-party backends. So for example, like NVIDIA CUDA backend, ROC, Intel Level 0, OpenMP, whatever, and so on. This with SYCL 2020, we had it's been a big jump for the SYCL standard with various new features like manufacturer memory, built-in reduction support, native API interoperability, and so forth. However, when having so many features, plus the idea that we have third-party backends plus multiple compilers, just kind of complicates all the validation part, as we have very multiple combination of things that go well, or those can also go wrong. So our work was on extending, in this case, the SYCL-Bench benchmark suite to include SYCL 2020 benchmark. SYCL-Bench is a benchmark suite for SYCL, originally designed for SYCL 1.1, and so our work was to extend it to add SYCL 2020 specific benchmark. In particular, our objective was to characterize both SYCL 2020 feature and on HPC GPU hardware, and also to evaluate the performance of novel feature and how SYCL implementation actually implement those features nowadays. We have quick recap of 9 new benchmark, 44 configuration, and bunch of features. We will not go over all of this because for time constraint, but just gonna see a bunch of them. Quick note about we just use the two major SYCL implementation at the time at the moment, which is Active CPP and Intel DPC Plus, and in this case 3 vendor GPUs NVIDIA, as NVIDIA for the Tesla 100S, for AMD ME100, and for Intel the Max 1100. So we're just gonna with the patterns. Okay. So first pattern we're gonna see is USM. In this case, one of the benchmark we're gonna have a quick overview is the host device transfer. As I said, we don't go all through all of it. We go for time constraint. So this is one of the first benchmark. Is just it just used it to simulate different offloading scenario. The idea is that to simulate a classic host device offloading scenario. So we have we exploit the different USM allocation capabilities. So by explicitly copy the data to the device, or just using the direct allocation, depending on if the USM allocation is available or not, is accessible or not to the specific device. The benchmark is parameterized with an instruction mix parameter. This basically regulates the ratio between the host device instruction ratio. So for example, if you have an instruction mix of 50, means that the device is doing 50x the instruction that actually the host is doing. So the structure is very simple. We have so allocate, we copy the data on the device, we perform something, we copy the data back, and then we perform such a NOS kernel. And the idea is this to measure the when a USM allocation is more suitable depending on the code structure. So this is first plot we're gonna see. On the X side, we have the instruction mix. So it is from 1 to 6, and on the I side is just the execution time. We use both device, host, shared with prefetch, using the SYCL prefetch keyword from SYCL 2020. And this plot here is the same plot, but just we measure the speed up between the shared with prefetch. So something about those plots. So in the first one, we can see that while the various allocation device and shared allocation almost constant during the time, like the host allocation just goes very high in time. But it's interesting to see that, for example, like for low instruction mix, the host allocation actually can outperform the device allocation, at least, for example, for an NVIDIA device. For example, like just when you have like an instruction mix of 1, which means that basically the host, the device and the host is doing like the same number of operation, we have like host operation performance even better. Like we need, for example, like 4+ instruction mix to match for the shared allocation to start to perform better than the host allocation. So we pay a lot the initial override in the allocation for the shared one. Some other interesting part from this experiment. We have on AMD, we have like the host allocation performs quite better than the shared one for at least until like 6 instruction mix. It's gonna continue like that until like 8, 9, etc. So this probably due to some problem with the MD, in this case with the shared allocation. Note that we just have the prefetched shared allocation, not the one without, because we're like on our machine like was having problem when using the automatic migration of operation between host and device without the prefetch. So yeah. And that interesting part was about the Intel hardware, that shared allocation basically comparable to device allocation. That with this happen because like on Intel hardware, like the data for shared allocation are moved at full allocation granularity rather than a page granularity. So in some cases, it's cannot be overlapped with device allocation. And yeah, and we can also see that here, like speed up this like this plot that basically the speed up with over the prefetch of the shared prefetch compared to the shared without the prefetch. And what we see on the Intel hardware, on NVIDIA hardware, we have like around 1.3 speed up compared to the other one. Instead of the Intel hardware, just like flat. No, it does nothing changes. Second pattern is reduction. So we know like in SYCL we have 2 kinds of reduction. So it's kernel reduction, which is like kernel level, and Khronos Group one. And group reduction, so that we can use inside the kernel one, which can be like a group, work group, or subgroup level. And yeah, we need a SYCL reduction that work with any SYCL support type, and can be like a kind of trick to implement. It's maybe not in a trivial way, but it can be complicated to optimize. SYCL-Bench originally didn't have like a reduction benchmark, so we added some benchmark for that. In this case, the benchmark is basically a kernel reduction and work group reduction, and is parameterized with the coarsening factor, which means basically changes the number of elements that are computed by each thread. And we compare it against a local memory reduction using just atomic in the end. So yeah, let's see some of the results here. This is like the results for 4 type, int32, 64, and floating point 32, 64. The different hedge depicts different implementations. So left is SVP, and right is the Intel TPCL plus, and different color is a different one. So some points here. We see that TPCL plus is not really influenced by, in this case, by coarsening. So the coarsening factor, augmenting it doesn't really give a lot of performance improvement, while instead this is required with adaptive CPP. And this happens because like TPCL plus actually internally, when you use like zero range parallel for, not in the range, automatically applies coarsening. So just take the old data, just try to spread your reduction all over the GPU, and then just cut it in case it doesn't fit the execution, just apply third coarsening. That's right. Interesting to see that in our implementation we have that with using kernel reduction, we managed to apply to get 2x speed up, but with DPC and WCVP compared, for example, to group reduction and also to local memory reduction, which means that like the implementation is quite good. And instead, like DBC++ group reduction, we're on par on local memory reduction, probably because yeah, for that. Third pattern, like the in order queue. I mean, in order queue is a very kind of simple simple features, just like we have the command executed in a FIFO order instead of like the classic out of order implementation. The interesting part is that as commands are executed in a FIFO order, there's some kind of interesting optimization that can be exploited. Like for example, we don't need a lot of the tracking dependency tracking system. For example, like we have like we're in a single queue environment. We have like different kernels that with the like dependency on the data. We don't really need to compute if which kernel depends on each other. And also, like part of the SYCL task graph, in theory, construction can be omitted as it's just like, it's a FIFO order. So the idea was to measure the, in this case, to measure the, using the both memory model like USM and buffer accessor, measure what happened on the scheduling part. So also measure the optimization happen on the scheduling part. So the kernel is just, the benchmark is just, is basically made of like 3 USM or buffers, just like using this additional kernel or NOP kernel, and one after the other, we try to measure the latency of the kernel. So and try to check if the implementation exploits some optimization on this side to improve the scheduling latency. These are the results. Yeah, we have the same plot twice, basically because if you can see like on the right, the MD for DPCS plus is gone here. This happened because like we have kind of a high override on the DPCS plus on MD when performing this benchmark. We're not extremely clear what is happening. This happened both with both the DPCS plus and also also for accuracy. So only for DPCS plus, and not extremely clear why. But we're working on it. And so we just showed the same plot twice for readability purpose. So for the USM out of order, because we also use the USM out of order to make for a fair comparison, we manually build the task graph using the SYCL depends on function. And interesting enough, when using in order queues, the majority of the improvement comes from the fact that the depends on is not used, of course, for the in order one, and we have like up to a 4x speed up using in order queues on USM. Surprisingly enough, when you set on accessor, where actually the major achievement could in theory major improvement could be achieved, we have like none or almost none improvements on that. So that string implementation doesn't really exploits or applies additional optimization when using in-order queues in this case. Yeah. Pattern 4 is specialization constant. So specialization constant allows you to inject basically runtime values as constant in device kernel. When you do that, like the kernel is JIT compiled, and just all the optimization pipeline is run with all the constant propagation, etc. And unfortunately, of course, this requires additional in theory JIT compilation time, and also recompilation each time the specialization constant is changed, of course. And depending on implementation, it can be implementation. It can be backend specific depending on, of course, the implementation strategy. We introduced a benchmark for this. Is a stencil. It uses the stencil as some parameter that can be either dynamic, like just runtime values, constants per, or so CL plus constants per, or specialization constant, and with an inner loop to increase the competition, to just increase the competition level. And so let's go to results. The plots here, we have it shows the runtime, like runtime compared relative to the execution relative to the dynamic. So dynamic is basically used as a baseline. So we just the fully dynamics and specialization constant and the constants per. On the left, we have in the Intel GPU. We see that basically when we use the specialization constant, the results are basically overlapping with the constants per, which means that whatever is happening, so something is happening, actually working pretty well. However, this is not what's happening instead on NVIDIA hardware or AMD hardware, which is with NVIDIA we have also like a tiny overhead for running it, so just kind of lose performance apart from that some outliner. And on AMD, that's the same thing that happened. Of course, this thing we can also see that with the last plot. This is the execution time relative to the median, which means that like relative to the median, how much time does it take? And this in the x of there's typo, sorry, is the number of the run. So it's like or the first run, the second run, third run, the fourth, and the fifth one. And we can see that with on both on Tesla, on NVIDIA and AMD, the execution time also is every time the same. When instead on Intel hardware, the first execution time takes way more time, up to 600 times more. So in this case, the execution time was like 2 milliseconds and takes like 600 times 2 milliseconds. So it really depends. It can be a huge impact in case the kernel, it's like you have like a very, very small kernel in this case. Okay, so it was way too fast. Way too fast. Oh, sorry. So to summarize, we was like the first benchmark suite for SYCL 2020, 9 new benchmark, 40-word configuration. Some of the points that we have here. So that basically the right USM allocation depends on the scenario. We see that like host allocation can actually work pretty well sometimes, and that actually is depending on the ratio between the operation and the host of the device. Or in order queues can significantly reduce the scheduling time in USM. No particular effect on accessor. Specialization constant has some problem to work on NVIDIA and AMD. But at the same time, compiler maturity seems to be improving. Like this, like there are no very high differences between the last we had like DPCS plus or adaptive CPP, the benchmark in which we had implementation for both of the implementation. So this was that. All of it. I thought it was like longer, or it was a bit fast, but that's it.
Any insight into why the out of order queues are slower, or does anyone in here know?
So okay, what do you mean in this case?
Just in order is faster. What is there an explanation for why? Like under the hood.
Okay, so basically I was too fast on this. So the for the USM, most of the benefits comes from the fact that I would say that for USM out of order, we manually build the task graph using the Penson, and basically like when you use in order, you don't need it, you remove it, and we have like this use speed up. Instead for accessor, this of course it's just accessor just build the task graph internally, and that seems to have any. I mean, if you see for accessor, that seems to have like an important speed up in general. So that's actually this was the point that just doesn't do that much. These are, I mean, with on AMD instead this happened with TP+ also for adaptive CPP. But if you see that also with adaptive CPP, AMD just way higher than the others. So we just suppose that something is happening. I think this speed up that we have here, also with accessor, which is the only place which is happening, is related to the issue that is also in the other in DPCL+. Is somewhat related. We're not exactly sure what's happening, but I think it comes from that.
To answer your question, I think it makes sense that the fact that you use in order or out of order queue for accessor doesn't change anything from the latency point of view, because the accessor, regardless of the queue or not, still need to do all the check for dependencies and stuff, right? So you don't expect to gain anything if you're using accessor to use in order. Expect super smart implementation who knows that you are initially is only one in order queue and you can maybe bypass any check. But at first approximation, it makes sense to me that the schedule, the overhead is due for handling all the dependency, and they are independent of in order of order queue when you are using accessor.
Yeah, I can take a stab at adding some context to this too. So for the implementations on the CUDA and HIP runtimes, the primitive exposed in CUDA and HIP is an in-order stream. So in-order queues, one-to-one mapping to that. Very, very simple. out of order queues, you have to do something more complicated in your runtime, assuming you don't want your out of order queues to really just be in order. So either you need to have multiple streams that your runtime's tracking, which can have overhead. And in the case of like the CUDA runtimes, it's actually not that bad. Someone mentioned this earlier in this week, if you're here, maybe, yeah, so AMD's even weirder because in SYCL, it's implementing it on a HIP in-order stream, but HIP is implementing in-order streams on out-of-order queue concepts in HSA. So you're getting this like double emulation hit in some sense.
Have you ever considered adding equivalent native implementations, like a native CUDA implementation for comparison of some of these benchmarks?
We considered that, it was just we couldn't like time related for time constraint. Just the idea that also to measure the comparison with the we planned to in the beginning to also have like the comparison with the native implementation. It was just a lot of work just in general, just way to do that. But yeah, it was an idea.
I'd like to hear if the room feels like there's value in that, other than my use case certainly has value in it, but I don't know if it's applicable to others as well.
So, I mean, my opinion as one of the co-authors of this paper, and also one of the co-authors of the original previous publication about SYCL-Bench. So the idea here is to provide a benchmark suite that is valuable for SYCL implementations to micro benchmark behavior of SYCL functionality. So therefore, the focus has always been on SYCL and providing SYCL functionality. And many of the benchmarks that we have in there perhaps don't even have a direct equivalent in native models and these kinds of things. I understand that for reference, it could be useful for specific things like how much more overhead does SYCL add over directly submitting to CUDA stream. I think for specific benchmarks, it could be useful, but I think it requires quite a lot of work because the build system needs to be much, much more complicated. If you then also need to build native CUDA or HIP benchmarks, and you need to be really careful and thinking about, okay, where it's actually possible and useful to add such benchmarks.
Yeah, to continue on this debate of is this useful to benchmark with native backend? I think when you ask this question, what you are asking is, what is the overhead of the SYCL runtime? Because at the end, you assume they are doing the same CUDA call when Axel is saying, when it is possible, you expect a one-to-one mapping. Like, for example, if you use, like James say, in order queue, you assume that they are mapping to one stream and you do a queue mem copy, you assume they will do a CUDA mem copy, whatever. So what you're asking is how long the C++ runtime, SYCL runtime is overhead is giving you. And I think to answer this question, what we really need is some introspection capabilities, some callback inside the SYCL runtime. So you can develop tools to be able to measure how long this overhead is, because you can already profile CUDA, you can already profile HIP, you use cuprof, and you will be able to profile these kind of things. So what we need is to be able to have callbacks. So then you can develop tools who have like cuprof. On the same timeline, you will see your call to CUDA and your call to SYCL, and you will see the overhead between the two. I think maybe this is what we are missing, a little of introspection inside the SYCL runtime. And I think we need to work on standardize this, like OpenMP tool, for example, if you are familiar with OpenMP or this kind of thing.
Did you have any insights on how the performance of the SYCL one-to-one features changed? Like, I guess I didn't read the original SYCL-Bench paper, but you did the benchmark on SYCL one-to-one. And then did you like see any changes on like, I don't know, performance between implementations of the original, for example, buffer accessor features between when you were doing the first SYCL-Bench implementation and now the new one? Or new benchmark runs?
We didn't really we just focused on the new feature, which is generally like for example, like all the SYCL one-to-one benchmark is still written in a one-to-one style. So we didn't like just run it. Of course, we expect like the performance to be better, like just because like implementation are improving on that side. But to be specific, we don't have like like new results specifically on those benchmarks. As you can see that.
All right, thanks.
Can you go back to the USM slide?
USM?
Yeah, I think the first pattern.
I suppose this one.
Yes. So think in the middle, there's this AMD MI100. So I was
Yes.
wondering if you did turn on the special hidden XNAG kernel parameter.
Yeah. Okay. So in general, so to give more context, also in the paper about that, like we tried it. So in first, this one is with XNAG disabled. Okay. So and actually we have like problem when we were like running when we were doing the run. So it's actually using the automatic translator. It was not really working. We switched it up to XNAG. It was working, and then sometimes it was sometimes it was working, and sometimes it was completely not. So depending on the time and some stuff, it was sometimes completely crashing the machine like randomly. So it just was very unstable. Just so that he decided to, instead of like start to debug what was happening, because we know that stack can be unstable and sometimes we just decided not to include that, not to enable that.
So on a good day, AMD works.
On a good maybe.
Okay. Any last questions? We still got a lot of time. Oh.
Okay. Thank you.